beta e raised to, what is xi beta, right? Sure? Right, so from here, what do you have? You have, look here, pi, see, from here, so from here, what do you have? Okay, from here you have pi, okay, is 1 minus pi, okay, e raised to xi beta. Right, now you see what's happening? Is this clear? Sure? See, assign array. Have a pi upon 1 minus pi, right, is e raised to xi beta, right? Sure? Right? Or here, yeah, here logic is pi is equal to lambda xi beta, right? So pi upon minus pi is this, okay? From which it follows that pi is 1 minus pi e raised to xi beta, right? Sure? Okay? So what will be the derivative of this? So dabba pi by dabba xi is equal to what? Beta 1 minus pi into e raised to xi beta, right? Now what is e raised to xi beta? Pi upon 1 minus pi, right? It's pi upon 1 minus pi it should be beta pi, no? No, it, hold on. So pi is equal to e raised to, say, x dash beta 1 plus e raised to x dash beta, okay? Right? Now if you differentiate this with respect to beta, differentiate with respect to xi, what will you get? Yeah? Because what is, what did you get? Yeah, you have to do the u by v rule. But it's easier to think of this pi upon 1 minus pi, okay, as equal to e raised to xi beta. So pi is equal to e raised to xi beta 1 minus pi. So derivative of pi with respect to xi is beta e raised to xi beta 1 minus pi. But e raised to xi beta is pi upon 1 minus pi. So actually pi 1 minus pi should cancel and you should get beta pi, right? You should actually get beta pi. 1 minus pi will go, right? Yeah, but why are we getting pi into 1 minus pi there? Why is there a 1 minus pi? Meaning, of course there is a problem. Yeah? See, there is a problem. The problem is like this. Okay, the problem is like this. Okay, the problem, friends, is like this. Okay? So we have pi, okay? I'll tell you where the problem is. Where the problem is. Pi is equal to, so 1 minus pi is equal to e raised to x beta. Right? So pi is equal to e raised to x beta 1 minus pi, which will of course be e raised to x beta 1 minus e raised to x beta. Right? Now, because pi is, yeah, no, it will be pi, so it would be e raised to x beta 1 plus e raised to x beta. Right? Now you have to differentiate the two. right? You have to now differentiate this with respect to beta and see what you get. With x. Differentiate this with respect to x and see what you get. Differentiate with respect to x and see what you get. So this is what? This is e raised to xi beta into 1 plus e raised to xi beta minus e raised to xi beta upon 1 plus e raised to xi beta, right? This is what? This is e raised to xi beta into 1 upon 1 plus e raised to xi beta, right? So now you have to do a chain rule and solve. So basically PQ, right? You can use, sure. So this will be e raised to xi beta upon 1 plus e raised to xi beta as defined, right? Now can you use the UV rule? So differentiate this with respect to xi. What do you get if you differentiate with respect to xi? Well, if you do that, you will get p into 1 minus pi into beta j, okay, into some value of beta, which you can try as homework now, right? Okay. So now, so basically now, if you have an estimate for pi, how will you estimate pi from the data? See, if you have data and 30 people out of 100 are working, you would say pi is 0.3. Right? If you have data and if you have out of those 100 people in the data, 30 are working, then you would say pi is 0.3, right? So you will put, so basically in our data, if you put instead of y, so pi is equal to y bar because that would be the average, no? If you sum up all the individuals, it will be 30 upon 100, so pi will be 0.3. If you substitute these values here, you get the value of pi equal to minus 0.202446. Yeah? Because y bar here is 0.456. 45% of the people in the sample were working. So instead of y bar, if you put 0.456 and this continues to be 1 minus y bar because that's our estimate and beta j was found to be minus 0.81504, you get the value of the LPM as, you get the value of this derivative as minus 0.2246, which is actually quite close to the linear LPM model. For the LPM model it is minus 0.16, whereas for the logic model it is minus 0.22446, right? Okay. Now the important thing is, this is okay, but you can't do it every time. You are interested in understanding how the probability of participation changes with income. So at various levels of income, basically you have to calculate this, right? If you want to really calculate that probability, what will you have to do? You have to say that the probability yi is equal to 1 is equal to e raised to alpha plus beta xi plus e raised to alpha plus beta xi and put various values of xi and see what happens to this probability, right? The next package that we are going to use in R essentially does this calculation. Okay, so instead of calculating these marginal effects every time, what the next package that we are going to do, okay, there is a package called effects, the library called effects, okay, right? I am going to use these effects to plot the effects. Now see what does this say? It says this tells you how the probability of participation decreases with income. As income increases, the probability of participation declines. How do you arrive at that point? E raised to alpha plus beta xi upon 1 plus e raised to alpha plus beta xi, you keep on plugging the values of xi and you get the probabilities of yi. You get the probabilities. Because the coefficient of income is negative, as income increases, the probability of participation keeps on falling, right? As age increases, the probability of participation goes on declining. Yeah? As age increases, the probability of participation goes on declining. What can you say about education? As education increases, what happens to the probability of participation? Increases, but by a very small amount. If you are completely uneducated, there is a 40% chance that you will be working. If you are highly educated, there is around the 50 to 53% chance that you are. So it doesn't really increase so dramatically. That's why the coefficient of education was not very significant. What do you think about young kids? Yes, if you have 0 young kids, then you are about 60% likely to work. But if you have 3 young kids, you are less than 10% likely to work. Okay? Old kids is very small. So if you have 0 old kids, you are about a 45% probability to be working. And if you have 6 old kids, then about 43% chance that you are working. So not really much of a difference. Okay? Foreign, if you are a non-Swiss person, there are about a 30% chance that you will be working. If you are a Swiss person, then there is almost a 70% chance that you are working. Right? So being foreign is of course important. And these are just effects which are plotted from that formula.
But sir,
yeah.
The foreign part, it can be that because that guy got a job, he came to in that region, hence 70% of foreigners are employed.
Yeah, it basically says that 70% of the foreigners are employed here. Right? What it essentially says, but what it says is that if you take a group of Swiss people, if you take a foreigner and a Swiss who are exactly identical in all other respects, including number of children, young, old, kids they have, income they have, education they have, age they have, then a foreigner is about 70%, the probability that he is employed is about 70%, whereas the probability that such a Swiss person is employed is around 0.3%. Right? So it's like that. Okay, so how do you test these hypotheses? How to test the beta coefficients? The Wald test. Wald test is what? Beta hat minus beta upon the standard error of beta whole square. Right? Because the null hypothesis is beta minus beta hat, beta star is 0, so it's beta hat upon the standard error of beta square. This is, as you can see, this will be a chi-square. Because it's a standard normal, no? Standard normal square. This is a chi-square with 1 degree of freedom because it's a single chi-square. Right? Now, this is what we call McFadden's pseudo-R square, for which Sid wanted a reference. Right? Okay, where the numerator in the second term is the log likelihood of the fitted model, and the denominator is the log likelihood of the model containing only the intercept. So the unrestricted model versus the divided by the restricted model. Okay? The unrestricted model, the log likelihoods, remember, the log likelihoods will be negative. Okay? So basically the basic idea is that the log likelihood of the unrestricted model would be bigger than the log likelihood of the restricted model. But because this is a negative number, the bigger would actually be smaller in absolute value. Minus 20 is a bigger number than minus 200, right? And therefore this ratio, where is that ratio? Yeah, this ratio, okay, is the ratio of the restricted likelihood to the restricted log likelihood to the unrestricted log likelihood. Okay, restricted log likelihood, unrestricted log likelihood. The larger is the restricted likelihood related to the unrestricted likelihood, the larger will this ratio, the smaller will this ratio be.
So you said LR will be greater than LUR.
Yeah.
But because the negative values we interchange.
Yeah, we interchange.
Then what do you say?
See, so the larger is this. The larger is this related to this. So suppose this is minus 20 and this is minus 200. Smaller will this ratio be? Right? Sure? And therefore this fraction will be closer to 1. Whereas if the log likelihood of the restricted and unrestricted are identical, then this will be 1 and the R square will be 0. That's why this is called McFadden's pseudo-R square. Why pseudo-R square? Because the usual R square is total sum of squares, explain sum of squares by the total sum of squares. But obviously with a binary dependent variable, you cannot have to have a total sum of squares and all that, because your data, your scatter is going to be like this. No? You're going to have y, x, and either the values are all 0 or the values are all 1. Right? So you're not going to have a scatter. And therefore you can't have the usual R square. This is called McFadden's pseudo R square. Right? This is called McFadden's pseudo R square.
So conclusion will be that R square is 0,
We mean that there is no difference between the restricted and unrestricted model.
if R square is 0.
R square is 0. Yeah. Okay, so in this case, what do? I do the models, right? So think of this, participation as dot numeric. The first model, GLM, is the participation model, regressed on all data. Right? In R, you don't have to write all the data down if you want to do it on all. It's just a tilde and a dot would regress everything on all, on everything. This says mod 0 is update mod. So take this model, but change it. What do? The formula is regress participation only on a 1. That is only on a constant. Right? So this is the restricted model. Probability of yi is a constant, is what we are saying. Because the design matrix, the constant 1, 1, 1 stands for constant in the x, right? Okay. So this is the model. So this is mod 0. Now this takes the log likelihood of the original model, the unrestricted model, divided by the log likelihood of the restricted model. The log like command in R will take the log likelihood of the restricted of a particular model object. Right? So this extracts the log likelihood of the model here. This extracts the log likelihood of the restricted model. This forms as dot 0, which is called 0.1250191. It's not a measure of the fit. It's a comparison of the likelihoods. That's you don't because there is no question of a fit here, no? Because the data are either 0 or 1, so you can't have a fit. Right? So yeah.
Can you explain the command formula equals to dot tilde 1?
Yeah. Formula it says what this command says.